So let's work out on this problem about hydrazoic acid. I like this problem because it actually integrates everything that we have learned so far with weak acids and weak bases. And in this problem, you have 0.200 molars of hydrazoic acid. You're given the Kb for the azide ion. And you're asked here to write the balanced equation for this reaction. First, identifying the conjugate acid-base pairs. Okay, so to do that, let's write an equation in which hydrazoic acid is in the presence of water. Okay, water there should be the base. So formula for hydrazoic acid is HN3, okay, aqueous, plus water as a liquid. And it's in equilibrium with H3O plus, and then that will be aqueous as well, plus azide ion. Okay, so again, hydrazoic acid behaves as an acid. It actually gives up a proton for water, which here acts as a base. Okay, and when hydrazoic acid gives up that proton, it is converted into its conjugate base. Okay, so azide here is the conjugate base, and hydronium should be the conjugate acid for water. Okay, so that's basically the first problem. The next one is you want to calculate the pH of the solution, and for there we're going to actually set up an ice table. Okay, with with this reaction that we have just written. Okay, so to set up this ice table, the only information that we're given is the initial concentration of hydrazoic acid. Okay, and then ignore water. This should be 0, 0. And then for the change, this is going to be minus x, plus x, and plus x. And then this one should be 0.200 minus x, then x, and then x. Okay, let's just assume that when we write the expression for Ka of hydrazoic acid, the concentration of hydrazoic acid at equilibrium is roughly equal to 0.200. Okay, now again, the next thing that we have to do here is to express or write an expression for Ka of hydrazoic acid. Now we're not given that value though. The only information that we're given is the Kb of the azide ion, which again, remember, is the conjugate base of hydrazoic acid. Okay, of hydrazoic acid. And this Kb expression is derived from this equation when N3 minus is in the presence of water. So the azide ion in the presence of water, okay, should accept an electron from, should accept a proton from water behaving as an acid this time to generate hydrazoic acid, HN3, and then OH minus. Okay, and again, if you write the equilibrium constant for this one, that will just be Kb is equal to the concentration of hydrazoic acid times OH minus, okay, divided by the concentration of the azide ion, which is again not equal to this Ka value. But since we know that that hydrazoic acid's conjugate base is the azide ion, then using Ka times Kb is equal to Kw, we can actually calculate for Kb of we can calculate for Ka of hydrazoic acid using the Kb of the azide ion. So if we rearrange this, that becomes Ka is equal to 1.0 times 10 to the negative 14. Okay, and we have written that the Kb for hydrazoic acid is 3.98 times 10 to the negative 10. Okay, so that's 3.98 times 10 to the negative 10. And this should give you 2.51 times 10 to the negative 5. Okay, and then to solve for x, okay, we can write finally now the expression for we can now finally write the expression for Ka. Okay, we now have a Ka value. So, and then again, let's apply this assumption. So that will just be 2.51 oops, sorry about that, 2.51 times 10 to the negative 10 is equal to the concentration of hydronium at equilibrium is given as X. The concentration of azide at equilibrium is also given as X. And then divided by reactants, which for this case is only hydrozoic acid. Okay. If we solve for this, we're going to get a value of X is equal to 5.03 times 10 to the negative 6. That's X squared, by the way, if we simplify this. Okay. And then solving for X, we get 0.00224 molar, which remember is equal to the concentration of hydronium ions, okay, and also equal to the concentration of the azide ions, okay. And then we're asked to calculate for percent dissociation. If we get a value more than 5% for percent dissociation or percent ionization, then we can just say that our assumption that this one X is negligible is valid. Okay, so here the percent dissociation or ionization, I think, is what I put in the problem, should be 0.00224 molar divided by 0.20, okay, times 100%. And this number actually gives you 1.12%. So in this problem, not only does it give you the percent dissociation, but it also means that our assumptions that X is negligible is valid. So assumption that X is negligible is valid. All right.